we present a novel representation of volumetric videos, which enable users to watch dynamic scenes from arbitrary viewpoints in real time. This is the agenda of this video. We will first describe the task setting, and then introduce related works. Subsequently, we will describe our key idea, the detailed steps of our approach, and the benefits it offers. Finally, the experiment results are presented. Our goal is to perform novel view synthesis of dynamic scenes. The input is multi-view videos, which are typically captured by many synchronized cameras. The output is a free viewpoint video. This enables many applications, such as video conferencing, sport broadcasting, and remote learning. Recent advances in neural scene representations provide a promising solution for this problem. They represent 3D scene with neural networks, which can be effectively learned from multi-view images through differentiable renderers. A representative work is neural volumes, which models a set of RGB density volumes predicted by 3D CNNs. While neural volumes achieves impressive rendering quality, the volume prediction easily consumes large amount of GPU memory, limiting its ability to synthesize high-resolution images. NeRF instead represent 3D scenes with MLP networks regressing density and color for any 3D point, thereby enabling it to synthesize high-resolution images. DynNeRF extends NeRF to model volumetric videos by introducing a temporal latent code as additional input of the MLP network. A major issue of NeRF models is that their rendering is generally quite slow, because the process requires millions of costly network evaluations. To overcome this challenge, our key idea is representing 3D scene as MLP maps, which are predicted by a per-scene trained 2D CNN decoder. This enables us to represent volumetric videos with a set of small MLP networks, thus reducing the cost of network evaluation and significantly improving the rendering speed. Specifically, the MLP map is a 2D grid map, with each pixel storing the parameters of an MLP network. To represent 3D scene with MLP maps, we project any 3D point to the 2D planes, defined by MLP maps for querying the corresponding MLP parameters. In practice, we align MLP maps with the axis of the coordinate frame, and point is orthographically projected onto a canonical plane. The projected query point is assigned to a parameter vector through spatial binning, which is dynamically loaded to the MLP network. Here we adopt a small NeRF network to predict the density and color for the query point. Based on the MLP map, we are able to use a 2D CNN to represent the volumetric video. The network architecture is implemented as an encoder-decoder, where the encoder regresses latent codes from camera views, and the decoder produces MLP maps based on latent codes. Our proposed MLP map has two advantages. First, MLP maps enable real-time rendering. Instead of modeling a 3D scene with a single MLP network, we represent it as a set of small MLP networks, which effectively decreases the cost of network evaluation. Second, MLP maps work well with 2D CNNs. Because MLP maps are in the format of 2D planes, it enables us to adopt 2D CNNs as the decoder instead of 3D CNNs, which leverages the fast inference speed of 2D CNNs. In the following, we will present some experiment results of our approach. First, our approach allows for real-time rendering of volumetric videos. The rendering speed achieves 41 FPS. This is another result. As we can see, our approach produces high-quality renderings, even with fast rendering speed. Next, we present the qualitative comparison with a previous state-of-the-art method. Our approach significantly outperforms it. This is another comparison. Here are quantitative results. Our approach achieves best performance in terms of the rendering quality and speed on the NHR dataset. Thank you for your watching. Welcome to our project page for more information.